That meeting's weird. So you got a taste of this yesterday. We have, when it comes to anti-differentiation, limitations. Those limitations are, it's got to be something on our list. So it's got to be a power function. It's got to be one of those trig patterns we studied. It's got to be e to the x. It's got to be a to the x. It's got to be the specific pattern that matches inverse sine. It's got to be the specific pattern that matches inverse tangent. Those are the things we operate under. Now, yesterday, we did a little bit of algebraic manipulation. You'll recall we used the distributive property. We used exponents. We did different things to rewrite the way the integrand looked so that we would be able to perform anti-differentiation. So we do all those manipulations and we get a thing that looks like something that's on our list. That's the big idea. What we're going to be doing today is going into more depth with the thing we looked at the end of yesterday, which is substitution. That's another way of taking an integrand, modifying that integrand in such a way that allows you to have one of the anti-differentiation patterns. So for practice, you looked at something about inside and outside functions. Now, I will tell you, I'm not the biggest fan of thinking about things in terms of inside and outside functions because I don't think that's particularly helpful for figuring out how substitution works. Instead, usually the way I think it's helpful to think about it is not an outside function and an inside function. Well, this won't work out quite the way I hoped. Well, I think we'll call it outside function, but my other idea is not going to work here. So this is me changing ideas on the fly here. Instead of inside function, we're going to call it a function whose derivative is present, asterisk. All right. So our quest to understand substitution continues here. So looking at the example we're provided with, we've got an antiderivative of x squared times the quantity of x cubed plus 1 to the 4th power dx. And when it comes to doing antiderivatives, there's no products. We can't do anything with products as written. That's not on the list, remember? We got trig, we got some exponentials, we got the power function. We don't have this one. So what we need to do is transform the way this looks into a fashion that would allow us to do an antiderivative. Like, I want you to imagine this is what we were looking at. The antiderivative of x to the 4th power dx. How does that sound for antiderivatives? Is that something that's on the list of things we're allowed to do? It absolutely is. That is a power function, right? Power function, okay. So if we could take this integral and rewrite it as that integral, we'd be able to do stuff. So the way we're going to do that is by substitution. And substitution works by identifying a function and identifying the derivative of that function, asterisk. So, for example, if you were to take the derivative of x to the 3rd plus 1, you would get 3x squared, right? Okay. And 3x squared is pretty much x squared, isn't it? It's pretty much the same thing as x squared. like there's a tiny difference on there, that's what the asterisk is for. So that's a difference we can overcome with another piece. All right. So when you looked at the second one, they talk about an outside function and they talk about an inside function. So outside function. Actually, I'm just going to change the variables here to u. Imagine, if you would, this is the thing whose antiderivative we had. Could we do that? Could you do that antiderivative? Give it a nice look on there. Could you do that one? Sure, that's one we've studied. It requires some algebraic manipulation. 1 over the square root of u, we'd have to change it into u to the negative 1/2 power. Yes, that's what would have to happen there, and then it's a power function. Good to go. All right. So x squared plus 5x plus 1 is inside the square root function, correct? But more importantly, the derivative of x squared plus 5x plus 1 is present. What's the derivative of x squared plus 5x plus 1? 2x plus 5. 2x plus 5 is right here in the integrand. Agreed? Yeah? Okay. So substitution comes from this idea of thinking similarly to how a chess player plays. So if you don't know much about chess, maybe you do. Queen's Gambit is reasonably popular right now. But one of the most important advanced moves in chess is to be thinking several moves ahead. So I do this now with the intention of, depending on what my opponent does, of course, doing these things later. If my opponent does this, I would do these things. So it's the idea of building a strategy into the future. That's a really powerful thing just in life, having a plan or a goal. But the problem is we can't necessarily see where that's headed. So the analogy I'm trying to get you to work off of here is we're trying to think in terms of, I want to have an antiderivative I can do. That's what I want to have. And in order to make that work with this substitution technique, we have to be thinking a few moves ahead. Hold on a second here. All right, continuing. So check out this next one. This next one is the antiderivative. We have dx in the numerator, square root of x times quantity of 1 plus square root of x in the denominator. Sorry, that's cubed, okay? So here's what I want you to imagine. I want you to imagine that this one right here could be changed into this one. Check that one out. Antiderivative 1 over u cubed du. Can we do that one? Yes, we can. That's another power function, isn't it? Yep, we change it to u to the negative 3rd power. We can do that one, okay? Here's what's standing in our way. We have inside of that cube in the denominator 1 plus the square root of x. In order for our substitution scheme to work out, the derivative of 1 plus the square root of x needs to be in the integrand. So let's check it out. Is this in the integrand? It is, but it's pretty confusing, right? It's square root of x in the denominator. So how do those fit in? Well, take the derivative of 1 plus the square root of x. That's 0 plus 1/2 x to the negative 1/2 power. Yeah, that's the derivative, okay? If I change this, I could call this 1/2 times 1 divided by the square root of x. And that 1 divided by the square root of x is right there, right? That's 1 divided by the square root of x. That's what this thing is. So I can do an antiderivative for this, even though it's a quotient, if I change the way it looks with substitution. Okay, so last night you're doing inside functions and outside functions, right? So for the next one, outside function is something to the 3/4 power. I'm just going to call it u. What is inside of u to the, or what is inside of the 3/4 power function? It's x to the 4th plus 2x squared plus 7. More important than that being the, well, as important, I guess, is fair to say, the derivative. The derivative. You may be looking at that and you may be saying, no, that's not there, right? I'm comparing it to this part, right? That's what you'd be comparing it to. You're starting to get the hang of this. That doesn't match very well, does it? It actually does. That's what the asterisk is for. So there's some manipulations I can do here to this one. And for that matter, the previous one. And for that matter, the first one. That's going to allow me to actually perform these antiderivatives, okay? Check out the next one. This next one is a gross and disgusting one because it is an extremely difficult form of substitution, but we're going to look at it nonetheless. So this is where the inside and outside function makes sense, I think, for understanding what's going on here. Imagine that this was true. Could you do that antiderivative? Antiderivative of 1 divided by the square root of u du. Could you do that one? Is that on the list? So think about the list. Yeah, that's on there. That's a power function. Okay. What's inside of that? Inside of that is x plus 4. Now, I know that the derivative of x plus 4 is 1. But that's actually not going to be an issue. Okay. Number 5 is equally difficult, in my opinion. But if we think about it in terms of inside functions, I actually can't tell. That's like to the 9th power. We'll pretend it's to the 9th power. It actually doesn't matter. Pretend that we were looking at this. U to the 9th power du, that antiderivative. Can we do that one? We sure can. That's a trig function. What's inside? Inside is x squared plus 1. We would like to have a 2x, which presents a bit of an issue, I'd say. All right. Honestly, number 5 is a tomorrow type of problem, to be perfectly honest. Okay. So when you're doing substitution, those are the general things you think about. You try to think several moves in advance. You want to think maybe it's helpful to do it in terms of an outside function and an inside function, but the two big takeaways I want you to have here when we're trying to do this substitution technique. The first one is the result is something I can take an antiderivative of. And the second thing, and one of the key things to actually get to that point, is the derivative is present. And again, that is asterisk. Okay. This is a good place to pause real quick, see if there are questions. And we're going to switch over to some more manageable practice problems. So what do I mean by that? Well, that's not it. Here is the first one we're going to look at. That is the antiderivative of x times the square root of the quantity x squared minus 2 with respect to x. So we start looking at it, and I'm going to throw you a bone. I'm going to tell you that we're going to use substitution here, okay? I don't want you to, though, get addicted to using substitution, because substitution does not fix all of your problems. So if you're in a relationship right now and you're having problems in that relationship and you think you're going to go home and use substitution to solve that one, that's not going to help you. It's also not going to help you with all of your antiderivative problems. Those things still exist too. Substitution won't fix them. We're learning substitution though, so I'm just going to be specific and say we're using substitution here. So how do I know I'm using substitution? Because that's kind of the level you want to get closer to, right? How do you know when to use substitution? That's a really important thing to learn. So the first thing is, I know what's not going to work. I know I'm not going to be able to use one of those basic things. This isn't a power function. It's not on my trig list. It's not an exponential. It's none of those things. I can't do this antiderivative. But this has potential. What's the potential I'm thinking about? The potential I'm thinking about here is, even though this is a product, I've got x squared minus 2 inside the square root function, right? That's inside of that, okay? And there's two things that are true. The first thing that's true is I can do this antiderivative, right? Let's just pretend it's x. We're not going to call it x, but just pretend it's x. Could you do that antiderivative? Sure, you could do that. It's a power function. And I guess that's 3 ands. 2 x's here. Asterisk. Because I know you're looking at that right now and you're like, Mr. Lewkowski, you're crazy. The derivative of x squared minus 2 is definitely 2x, but 2x is nowhere in that integrand, right? There's no 2x in there. Okay, well, let me learn you. That is what we're after. Let me learn you. It's taking up too much room. You guys got to get yourself some smart paper so you can do that too. So if I use substitution here, and in general, what's used is u. How come? Tradition. Other reasons? Don't know, but u is typically what's done. U equals x squared minus 2. If I differentiate both sides with respect to x, on the left side, I get du dx because of implicit differentiation. On the right side, I get 2x. And additionally, there's two things that are true. The first thing that is true is if I multiply both sides by dx, I get 2x dx. And the second thing that is true is I'm allowed to, anytime I'm working with an equation, no matter what the circumstances are, I'm allowed to do the same thing to both sides. In this case, I am going to multiply both sides by 1/2, which means I have the following statement of equality. 1/2 du equals x dx. So let me back up, recapitulate. I've declared using this idea of an inside function. U is going to be x squared minus 1. That means I'm going to substitute for x squared minus 2, u. If I take the derivative of this equation I came up with respect to x using implicit differentiation, I get du dx. On the right side, I get 2x minus 0. And then, because I don't have a good match here between 2x and x, I'm telling you that we can make that happen by using our knowledge. Notice how I've color-coded the asterisk here. The asterisk is you're allowed to multiply both sides by a half and not change the value of the expression, correct? You're allowed to do that? Yeah, 1/2 is not a variable, we can do that. Okay, so check this out. This next part is optional. So you don't have to do that, but it may make it easier for some of you to process what's happening if we just think about how we can change the order. So I can take x times the square root of x squared minus 2 and say square root of x squared minus 2 times x. I'm allowed to do that. And this may line up better. So u is going to substitute or replace x squared minus 2. All right. So I'm talking about this. I'm talking about square root of u x dx. So that doesn't look very good at all. It's got u's and x's in it. It's pretty gross and nasty and wrong, okay? But I can, because I've already planned for it, make a second substitution. 1/2 du, 1/2 du can go right here. So if I use that, what I'm talking about then is this. Which, using just a teensy bit of algebra cleanup, now looks like this. All right, 1/2 is a constant multiple. I can multiply an integral or antiderivative in this case by 1/2. So check that out. If you started off with just this right here, picking back up after the service interruption, we can do this antiderivative right here because square root of u is u to the 1/2 power. So if I do that antiderivative, I get u to the 1/2 becomes 3/2, 2/3 u to the 3/2 power plus c. No writing plus c if you haven't already. Let's see which scrubs have not written plus c. Oh boy. Oh boy, I don't see a lot of plus c's on here. Okay, still at 0 days remembering plus c. There's always tomorrow. Maybe tomorrow will happen. All right, so we've got this, which is equal to 1/3 times x squared minus 2 to the 3/2 power plus c. Look at that. We've done it. How do we know we've done it? Well, you don't have to take my word for it. You could check this and confirm that this derivative right here gives you the thing we started with, but I'm not going to write it out. I'm just going to mention that if we take the derivative of 1/3 times x squared minus 2 to the 3/2 power plus c, we're going to need the chain rule. So it's going to be 1/3 times 3/2 times the quantity of x squared minus 2 to the 1/2 power. Take the derivative of x squared minus 2, you get 2x. 1/2 times 3/2 times 2x times 1/3 is x. Yeah, so that worked out gloriously. Very, very gloriously. Now, actually doing this on your own is not quite so intense. It's not quite so restrictive and difficult. But starting out, there's a lot of over-explaining that needs to happen in order for you to follow what's going on, I think. This next one, we're going to look at this 5th one here together. This one should go faster, I believe. So it's an antiderivative. That's an x squared times the square root of 1 minus 4x cubed dx, of course. So while you're writing that down, I know that you know that we're going to be using substitution here because that's what we've been practicing. Yes, substitution makes sense. But knowing that we're using substitution is not really a good reason when it comes to doing things on your own. So what are the types of things we want to be thinking about? Well, we want to be thinking about the things I mentioned already. So what is it I've mentioned already? There were 2 really important things. We want to be thinking about the end game. We want to be thinking about how the result should be integrable, meaning we can do an antiderivative. We should also be thinking in terms of, I need the derivative of a function. If you're not sure why you need the derivative of a function, looking back at the last one, the reason why was because this dx part, that's a problem. But I can make a dx if I take a derivative with respect to x. So checking out this next one, that's what we're thinking about. So it may be helpful to think in terms of inside and outside functions. It's helpful to think in terms of derivatives. But the main thing is, we know that our normal stuff, the list we have, isn't going to work here. And we had to change this into something that will work on the list. So imagine if everything except the square root was gone. Could we do that? We sure could. That's going to work. Okay. So that's what our goal is going to be. So we have 1 minus 4x cubed. That is inside the square root, yes? Okay. If I differentiate that with respect to x, I have 0 minus 12x squared, which, if I multiply both sides by dx, means du equals 12x squared dx, which is a little bit of a problem because we have x squared dx. We don't have 12x squared. But that is an eminently correctable problem because we can multiply both sides by a 12th, which means 1/12 du equals x squared dx. This is a good point to pause. So we've established that it is in fact -12, and once again, I'm an idiot. But we have also established that we can make the first substitution is anywhere there is a 1 minus 4x cubed, I can replace that with u. Anywhere there is an x squared dx, I can replace that with a -1/12 du. So we've got x squared dx right here and a u right in here. So we make our two substitutions. In case you're curious right now, is it always two substitutions? No, it's not always, but mostly it is two substitutions. Not always, but mostly. Okay, check that out. Is that an antiderivative you can do? Surely it is. Do so. I'm gonna pause here for questions. All right. So, how do you know when to use substitution? Well, we want to be thinking in terms of future moves. We want to be thinking about how the thing we have is not integrable, but if we were to replace some things, it would become that way. And the way we think about replacing those things is sometimes it's helpful to think of an inside function, but it's always helpful to think about the derivative of some function. So I look here and I think about how x to the 1/2, well, that's derivative is definitely not x to the 3/2 power plus 4, not even close. But the derivative of x to the power of 3/2 plus 4 is really, really close to x to the 1/2 power. So that's what I'm going to substitute for, the x to the 3/2 power plus 4. If I take the derivative of both sides with respect to x, on the left side using implicit differentiation, I have du dx. On the right side, I have 3/2 x to the 1/2 power plus 0. And if I multiply both sides by dx, I have 3/2 x to the 1/2 power dx on the right side, du on the left side, which is pretty much the same thing as x to the 1/2 asterisk. Why is the asterisk there? Well, think about what you could do so that the right side is exactly x to the 1/2 power dx. What could you do? You could multiply both sides by 2/3. If you multiply both sides by 2/3, on the left side, you have 2/3 du. On the right side, 2/3 times 3/2 is 1. So you have x to the 1/2 power times dx. So we have set up now two substitutions that are going to allow us to be able to do the antiderivative here. One of those substitutions is anytime we see x to the 3s power plus 4, we can replace that with u. The other substitution is anytime we see x to the 1/2 power dx, we can replace that with 2/3 du. So I've got, if I think creatively, x to the 1/2 power times dx right there. Yes, right, that's what I need. So that's going to be a 2/3 du. Oops, that's not a square root, that's the 9th power, sorry. So we're looking at that. My u and my 9 somehow ended up being almost identical. Don't ask me how that happened. You too may not learn all of my ways. Maybe one day. So take a look at that. If we started with that, could you do that antiderivative right there? If you had 2/3 times the antiderivative of u to the 9th power du, can you do that one? Absolutely, that's a power function. We got that. Okay. Doable. 2/3, new exponent is 10, multiplied by a 10th, u to the 10th power plus c, and then we are substituting for u again, the original statement. And that's because I'm actually going to simplify that. 2/30 is 1/15. The original statement is in terms of x. Compare your final answer to mine. Let me know if you have questions. I'm pausing the recording. So to be successful with this one I came up with, you need to be intimately familiar with the basic antiderivatives. If you're not, these are going to be very, very difficult. So when you look at this, you should start thinking to yourself, I wonder if I could make this look like secant times tangent, which is on my antiderivative list, right? The antiderivative of secant of x tangent of x with respect to x is, gosh, is it secant of x? Is it tangent of x? Who could know? Who could know? Oh, you're supposed to. So, inside function, 2x, 1/2 du, although there's another way we could do this, is going to equal dx. So dx, or u, is 2x. 1/2 du is dx. So I could think of this as 4/5 times the antiderivative of a 1/2 secant of u, tangent of u, du, which, according to multiplication, 4/5 times 1/2 is 2/5, and antiderivatives is secant plus c. Check your papers right now. Did you have a plus c on your final answer? You should have. If you do not, well, Friday is going to be unpleasant. All right. Let me pause here for more questions. Oh, before I pause for questions, quick reminder, you can always check your work by starting over with your answer and taking the derivative of that following the derivative techniques we studied for, well, Ultimately, it will end up being half the class, but for right now, most of the class. So I'm going to substitute sine of x with u because the derivative of sine of x is cosine of x, and I can do the antiderivative of u cubed. So if you ever wonder, how does Mr. Lewkowski look at a new problem he's never done before and know whether or not to use substitution? Those are the two things I think about. I think about what could I replace, and if I replace that thing, is that thing's derivative there? And do I get a thing I can do an antiderivative of? There's the three ands again, or the two ands, sorry, the two ands. So how do you do these? How do you know to use substitution? It's like that. Let me say that one more time and try to follow along. So I looked at sine cubed of x, cosine of x dx, and I thought to myself, well, that's not on the list, right? Sine cubed cosine, that's not on the trig list. Agreed? Not on the trig list? Okay, not on the trig list. So what could I do? Well, there's lots of things I could try, but I'm going to at least think about substitution here. And I said, you know what? Three things. First thing, if I replace sine of x with u, I would get u cubed. Second thing, I can do the antiderivative of u cubed. And third thing, the derivative of sine of x is cosine of x, and that's here. So I know I can substitute for those. So u is going to be sine of x, cosine of x dx. That is going to be du. So after substituting, I have the antiderivative of u cubed du, which is 1/4 u to the 4th power plus c. Excuse me. Or 1/4 times sine of x to the 4th plus c. Nice. Okay. We're going to do a little bit more with substitution here, but we're going to need our Chromebooks for that. But this is where the recording is going to end on our first day of substitution together.